Hi everyone, today we're going to share with you a transformative development in the field of large language model alignment, direct preference optimization. This presentation is roughly divided into four parts. Now let's walk into the introduction together. So what is alignment? Large language models are like unrefined genius. They gain vast knowledge from training data, but also absorb lots of extreme ideas, leading to unpredictable output. To ensure safety, alignment is implemented, a process to guide AI behavior toward human expectations. Before DPO, reinforcement learning based on human feedback was the gold standard. It is a very complex process. First, supervised fine-tuning teaches the model conversational formats. Then, human preferences are collected to train a reward model. Finally, PPO reinforcement learning is employed, allowing the model to refine its response strategies based on the scores from reward model. However, this approach suffers from two limitations: extremely complex and unstable architecture and huge computational cost. Thus, the proposed direct preference optimization approach is trying to launch a far more simple way, jumping directly from human preference to final policy. Next, my groupmates will guide you into the methodology part of DPO. Welcome.
Shall talk about the methodology, more specifically about the derivation of the DPO objective. Before we get in there, I shall talk about the RLHF pipeline first. It is divided into three stages. The first is fine-tuning the pre-trained LM model to obtain the policy of SFT, and then it goes to the reward modeling phase, where it generates several responses and use humans to annotate which is the preferred answer. And we use this BT model, and then the reward model is parameterized by predicting the human preference by minimizing this loss. So what this loss does is basically it penalizes the reward model if it gives a lower score, the winning or preferred answer rather than the losing answer. Then next is the RL fine-tuning phase. After getting this reward model, we guide the policy optimization by using that. We try to find this the reward, the answer of the reward which is as high as possible. However, it still sticks as close as possible to this original reference policy, which is the SFT policy. Then next is the deriving the DPO objective. Since the RLHF requires a separate reward model and performing a PPO-based reinforcement learning, the complexity is very high. Thus, we try to check the optimal policy and try to make some mathematical transformations here. And since this is max function, we try to change some of it into the minimization function, and we introduce a partitioning function, which is the Z here, so that it can become a probability distribution function, where it normalizes this reference, policy reference and the exponential of this reward. And then, since we see that this denominator does not have any relation to our training policy, and it has relation to the reference policy. So we try to define it as a modified base policy. We substitute this into the policy star, and we can see that this is the pattern of the KL divergence again. Thus, we can say that to produce KL, this is our it's still the same optimal policy, but it's modified to be like this. Since it is a probability distribution function, it will be in the positive range, and the lowest score will be 0. Which means to minimize this function, we need to make our training policy to be equal to our modified base policy. Since we already know that, the partitioning function, which is Z, is still computationally expensive to be estimated. Thus, we try to isolate this reward function first and see if we can plug it into the BT preference model. And we see that after isolating this reward model, we plug it in, and we can see that the Z is now cancelled out, which we can infer from this that the preference comparisons implicitly determine the reward signal. So we can bypass the explicit reward model training and directly optimize it. And we can see here that it is a sigmoid function, and thus this is our DPO objective. I will pass it to Imei. Thank you.
I'm Yimei, and I'll be summarizing the important aspect of this DPO training algorithm presented in the paper. First of all, the main objective of DPO is to directly learn from human preference data. Instead of learning a separate reward model and then use reinforcement learning, DPO uses preference pairs consisting of a prompt, a preferred response, and a rejected response. The key insights come from the paper's proof that reward information can be recovered from the language model probabilities relative to a reference model. Because of this relationship, DPO can optimize preferences without explicitly learning a reward function. The loss function compares how much more likely the preferred response is compared to the rejected response, while also considering the reference model. This reference model acts as an anchor to prevent the language model from drifting too far away from the original supervised fine-tuned model. After defining the objective, DPO updates the language model using preference pairs. For each prompt, the model compares a preferred response and a rejected response. It then computes a relative preference score based on the probability assigned by the current model and the reference model. This score is passed through a sigmoid function and optimized using classification style laws. The model parameters are updated through standard backpropagation, similar to supervised learning. An important characteristic of DPO is its dynamic importance weighting. If the model is uncertain about which response should be preferred, the gradient becomes large and the update is stronger. On the other hand, if the model already agrees with human preferences, the gradient becomes small and the update is weaker. This behavior allows DPO to focus learning on difficult examples automatically. Compared with PPO-based RLHFs, DPO removes the needs for reward model training, row-out generation, and value estimation, resulting in a simpler and more stable optimization process.
A traditional RLHF is hard to train, and the elder found that under the battery model, human preference depends only on reward difference. Mathematically, reward function differing by a promote-only term induce the same preference difference and optimal policy. This equivalence is a closed form optimal policy, rewriting reward as a log ratio of model probability. So the language model itself is secretly a reward model. In DPO, when we compute preference difference, the complex normalization term cancel out, so there's no unstable sampling. On the IMDP sentiment task, the elder plot the reward KL frontier. Reward achieved various deviations from the reference model. DPO strictly dominates both PPO and PPO-GT, which use ground truth rewards. This proves PPO's bottleneck is the RL optimization itself. Next, welcome Yuqi.
Next, the performance of DPO was evaluated on two tasks, which are summarization using the Reddit TLDR summarization dataset and a singleton dialog using the entropic helpful and harmless dialog dataset. A model performance is evaluated by sampling the output at different temperature ranging from 0 to 1. A win rate matrix is used, where the generated response is compared with the reference response using the GPT-4 as judge to decide which one is preferred. For the summarization task, 6 different methods are evaluated. DPO, PPO, and preferred FT are all fine-tuned using the same GPT-J SFT model. The result shows that the DPO achieved around 61% win rate at the temperature 0, which is higher than the PPO and best of n at their best setting. In addition, DPO is more robust across different sampling temperature, whereas the PPO performance degrades significantly as the temperature increases. Besides, the preferred FT shows a little improvement over the original SFT model. For the singleton dialog task, the DPO is trained from the PTR 2.8 billion model that is first fine-tuned using the preferred FT. The result shows that the DPO perform as well as or better than the other method at their optimal sampling temperature. Overall, the experiment demonstrates that the DPO consistently match or outperform this baseline while requiring less computational cost and converging to strong performance relatively quickly.
Next, let's look at how well DPO performs on completely new data. The authors trained the models on Reddit forum posts and tested them on CNN Daily Mail news articles, which come from a different distribution. As shown in Table 1, DPO achieved a higher GPT-4 win rate of 36% compared to 26% for PPO. Similar trends were observed at other temperatures. This result shows that DPO generalizes well to unseen data and can even outperform PPO under distribution shifts, despite not using additional unlabeled prompts. Furthermore, the authors conducted a human study to evaluate the reliability of GPT-4 as an automatic evaluator. They compared with two prompts, GPT-4 simple prompt and GPT-4 concise prompt. As shown in Table 2, although the simple prompt shows slightly higher agreement in some cases, it tends to favor longer and more repetitive summaries, making it less aligned with human preference. For example, the concise prompt achieved a win rate of 84% for DPO, which is closer to the human score of 58% than the simple prompt 47%. Therefore, the authors chose the concise prompt. Most importantly, the concise prompt reaches up to 85% agreement with humans, which is very close to the 87% agreement between human evaluators. This proves that it is a highly reliable automatic judge for the main experiments. In conclusion, DPO provides a much simpler alternative to traditional RLHF methods. Instead of using reinforcement learning such as PPO, it directly learns from human preference using a standard cross-entropy laws. Despite its simplicity, DPO achieves comparable and even better performance with minimal hyperparameter tuning. For future work, the author suggests that starting out of distribution generalization, reward over optimization, scaling DPO to larger models, improving automated evaluation methods, and extending DPO to other modalities such as image and audio generations. Lastly, for our overall insight, the true significance of this research is how it solves the instability of AI training. Traditional RHF is very complex and hard to control. DPO turns this into a simple classification problem. This makes training safe and helpful AI much more reliable and predictable. That's all for our presentation. Thank you.